Why is the order in dictionaries and sets arbitrary? I don't understand how looping over a dictionary or set in Python is done by arbitrary order. I mean, it's a programming language, so everything in the language must be 100% determined, correct? Python must have some kind of algorithm that decides which part of the dictionary or set is chosen, first, second, and so on. What am I missing?
Note: this answer was written before the implementation of the dict type changed, in Python 3.6. Most of the implementation details in this answer still apply, but the listing order of keys in dictionaries is no longer determined by hash values. The set implementation remains unchanged. The order is not arbitrary, but depends on the insertion and deletion history of the dictionary or set, as well as on the specific Python implementation. For the remainder of this answer, for dictionary, you can also read set. Sets are implemented as dictionaries with just keys and no values. Keys are hashed, and hash values are assigned to slots in a dynamic table. It can grow or shrink based on needs. And that mapping process can lead to collisions, meaning that a key will have to be slotted in a next slot based on what is already there. Listing the contents loops over the slots, and so keys are listed in the order they currently reside in the table. Take the keys foo and bar, for example, and let's assume the table size is 8 slots. In Python 2.7, hash foo is -4 quintillion 177 quadrillion 197 trillion 833 billion 195 million 190,597. Hash bar is 327 quadrillion 24 trillion 216 billion 814 million 240,868. Modulo 8. That means these two keys are slotted in slots 3 and 4 then. This informs their listing order. All slots except 3 and 4 are empty. Looping over the table first lists slot 3, then slot 4, so foo is listed before bar. Bar and baz, however, have hash values that are exactly 8 apart and thus map to the exact same slot, 4. Their order now depends on which key was slotted first. The second key will have to be moved to a next slot. The table order differs here, because one or the other key was slotted first. The technical name for the underlying structure used by Python, the most commonly used Python implementation, is a hash table, one that uses open addressing. If you are curious, and understand C well enough, take a look at the C implementation for all the, well-documented, details. You could also watch this Pick in 2010 presentation by Brandon Rhodes about how Python dict works, or pick up a copy of Beautiful Code, which includes a chapter on the implementation written by Andrew Kuchling. Note that as of Python 3.3, a random hash seed is used as well, making hash collisions unpredictable to prevent certain types of denial of service, where an attacker renders a Python server unresponsive by causing mass hash collisions. This means that the order of a given dictionary or set is then also dependent on the random hash seed for the current Python invocation. Other implementations are free to use a different structure for dictionaries, as long as they satisfy the documented Python interface for them, but I believe that all implementations so far use a variation of the hash table. Python 3.6 introduces a new dict implementation that maintains insertion order, and is faster and more memory efficient to boot. Rather than keep a large sparse table where each row references the stored hash value, and the key and value objects, the new implementation adds a smaller hash array that only references indices in a separate dense table, one that only contains as many rows as there are actual key value pairs, and it is the dense table that happens to list the contained items in order. See the proposal to Python dev for more details. Note that in Python 3.6 this is considered an implementation detail. Python the language does not specify that other implementations have to retain order. This changed in Python 3.7, where this detail was elevated to be a language specification. For any implementation to be properly compatible with Python 3.7 or newer, it must copy this order-preserving behavior. And to be explicit, this change doesn't apply to sets, as sets already have a small hash structure. Python 2.7 and newer also provides an orderedict class, a subclass of dict that adds an additional data structure to record key order. At the price of some speed and extra memory, this class remembers in what order you inserted keys. Listing keys, values or items will then do so in that order. It uses a doubly linked list stored in an additional dictionary to keep the order up to date efficiently. See the post by Raymond Hedinger outlining the idea. Orderedict objects have other advantages, such as being reorderable. If you wanted an ordered set, you can install the oset package. It works on Python 2.5 and up.
This is more a response to Python 3.41 a set before it was closed as a duplicate. The others are right, don't rely on the order. Don't even pretend there is one. That said, there is one thing you can rely on. That is, the order is stable. Understanding why there is a perceived order requires understanding a few things. That Python uses hash sets. How Python's hash set is stored in memory and how numbers get hashed. From the top. A hash set is a method of storing random data with really fast lookup times. It has a backing array. We shall ignore the special dummy object, which exists only to make removes easier to deal with, because we won't be removing from these sets. In order to have really fast lookup, you do some magic to calculate a hash from an object. The only rule is that two objects which are equal have the same hash. But if two objects have the same hash, they can be unequal. You then make an index by taking the modulus by the array length. This makes it really fast to access elements. Hashes are only most of the story, as hash n%len storage and hash m%len storage can result in the same number. In that case, several different strategies can try and resolve the conflict. Python uses linear probing 9 times before doing pseudorandom probing, so it will look to the right of the slot for up to 9 places before looking elsewhere. Python's hash sets are stored like this. A hash set can be no more than 60% full. Note, this load factor was previously 66%. It was reduced in Python 3.7. If there are 20 elements and the backing array is 30 elements long, the backing store will resize to be larger. This is because you get collisions more often with small backing stores, and collisions slow everything down. When the backing store becomes too full, it will be automatically resized to increase the ratio of unused space. A higher ratio of unused space means it's faster to find a slot when handling a hash collision. For small sets, storage will be quadrupled in size, and for large sets, 50,000, it will be doubled in size, source. So when you create an array, the backing store is length 8. Once it is 4 full and you add an element, it will contain 5 elements. 5 is greater than cube/5 middle.8, so this triggers a resize, and the backing store quadruples to size 32. Finally, hash n just returns n for integers, except for hash -1, which returns -2 because the value -1 is reserved for another usage. So, let's look at the first one. Len v_set is 10, so the backing store is at least 15 plus 1 after all items have been added. The relevant power of 2 is 32. So the backing store is, we have so these insert as so we would expect an order like with the 1 or 33 that isn't at the start somewhere else. This will use linear probing, so we will either have or you might expect the 33 to be the one that's displaced because the 1 was already there, but due to the resizing that happens as the set is being built, this isn't actually the case. Every time the set gets rebuilt, the items already added are effectively reordered. Now you can see why. Might be in order. There are 14 elements, so the backing store is at least 21 plus 1, which means 32. 1 to 13 hash in the first 13 slots. 20 goes in slot 20. $55 goes in slot hash 55% 32, which is 23. If we chose 50 instead, we'd expect and lo and behold, pop is implemented quite simply by the looks of things. It traverses the underlying array and pops the first element, skipping over unused slots and dummy entries, tombstone markers from removed elements. This is all implementation detail.
Arbitrary isn't the same thing as non-determined. What they're saying is that there are no useful properties of dictionary iteration order that are in the public interface. There almost certainly are many properties of the iteration order that are fully determined by the code that currently implements dictionary iteration, but the authors aren't promising them to you as something you can use. This gives them more freedom to change these properties between Python versions, or even just in different operating conditions, or completely at random at runtime, without worrying that your program will break. Thus, if you write a program that depends on any property at all of dictionary order, then you are breaking the contract of using the dictionary type, and the Python developers are not promising that this will always work, even if it appears to work for now when you test it. It's basically the equivalent of relying on undefined behavior in C.
Python use hashtable for storing the dictionaries, so there is no order in dictionaries or other iterable objects that use hash table. But regarding the indices of items in a hash object, Python calculate the indices based on following code within hashtable.c. Therefore, as the hash value of integers is the integer itself, the index is based on the number, height, num_buckets, 1 is a constant, so the index calculated by bitwise and between, height, num_buckets, 1, and the number itself, expect for -1 which its hash is -2, and for other objects with their hash value. Consider the following example with set that use hash table. For number 33 we have that actually it's. Note in this case, height, num_buckets, 1, is 8 to 1 equals 7 or 0 be 111. And for 1919. And for 333. For more details about Python hash function, it's good to read the following quotes from Python source code. Major subtleties ahead. Most hash schemes depend on having a good hash function, in the sense of simulating randomness. Python doesn't. Its most important hash functions, for strings and ints, are very regular in common cases. This isn't necessarily bad. To the contrary, in a table of size 2i, taking the low order I bits as the initial table index is extremely fast, and there are no collisions at all for dic's index by a contiguous range of ints. The same is approximately true when keys are consecutive strings. So this gives better than random behavior in common cases, and that's very desirable. Although, when collisions occur, the tendency to fill contiguous slices of the hash table makes a good collision resolution strategy crucial. Taking only the last I bits of the hash code is also vulnerable. For example, consider the list, I16 for I in range 20,000, as a set of keys. Since ints are their own hash codes, and this fits in a dict of size 215, the last 15 bits of every hash code are all 0, they all map to the same table index. But catering to unusual cases should not slow the usual ones, so we just take the last I bits anyway. It's up to collision resolution to do the rest. If we usually find the key we're looking for on the first try, and, it turns out, we usually do, the table load factor is kept under 2/3, so the odds are solidly in our favor, then it makes best sense to keep the initial index computation dirt cheap. The hash function for class int.
Jo, vänta senare. Jag äter som subscribing.